All right, so right now we're working on 2007 question 1, and this is the sled one that we did in class. And so we have this empty sled of that mass, and it's a constant speed. So knowing that it's a constant speed, we know that the forces that we're dealing with are going to be balanced because the sum of the forces is going to equal 0. So the sled of the hill is inclined at an angle of 15 degrees with the horizontal as shown in the figure above. So the first thing they want is calculate the time it takes the sled to go 21 meters down the slope. All right, so this is just a simple kinematics problem. So t equals question mark. Change in x is going to equal 21 meters, and we know that our speed is going to be this 2.4 meters per second. And we know that velocity is going to equal change in x divided by time. And just from remembering from our algebra, we can switch the v and the t so that t ends up equaling change in x all over v. And so now we just plug it in. So t is going to equal this 21 divided by 2.4. So 21 divided by 2.4 is going to give us 8.75 seconds. So that's going to be part A. Then for part B, it wants to, on the dot below that represents the sled, draw and label a free body diagram for the sled as it slides down. So we see that the free body diagram is actually on the other side, and so we see that it's going down at that velocity, but don't draw that arrow because that's an unnecessary line and they may even count it wrong if you draw it. But we just know that our velocity is going down to the right. That means that our friction must be going to the left because friction opposes motion. Our normal force is always going to be perpendicular. Don't draw this either, but I'm just showing you. It's always perpendicular to the surface. And our mg is always pointing straight down. And that's it. That's how you do part B. So next it wants to calculate the friction force on the sled as it slides down the slope. So we don't want to touch this again. So we're going to redraw our free body diagram over here. And let's just draw it so that we don't have to look at our page or turn our page like that. Okay, so let's just go ahead and draw it so that it looks like what we would turn our page. So we've got our normal going up, our friction going to the left, and then we've got our mg kind of to the side like that. So our mg to the side. And so it's looking for, what is this frictional force right here? And we see that this frictional force is in the x direction, so we're going to say sum of the forces in the x direction we know equals 0 because we have a constant velocity. And so our velocity is going to the right, but our friction is going to the left, so we're going to make that negative. But do we have anything else going the x direction? Well, yes, we do. We have this mg because the mg is not only pointing down, it's pointing to the right. And we see that this angle right here, that angle is going to equal that theta, theta right here, this 15. And the reason why is because we have got this right here. This is our mg. We see that's our mg. And we see that this is 15, therefore this must be 75 because this is 90. And so 15, 75 plus 90 is 180. And so we look and we see that we had to make this triangle right here. And so this triangle creates a 90-degree angle right there. And so we see that if this is 75, this is going to be 90 minus 75, which is 15. So we see that this angle right here with this new triangle that we had to draw is going to be 15. So we see that this angle is our theta, or our 15. We're just going to call it theta for now because we don't want to plug in numbers yet. And so we see that this is going to be our mg in the x direction. We've got our mg in the x, so we're going to say mg in the x direction minus our friction because we see that our mg is pointed to the right, our friction is pointed to the left. The reason why we're sliding down this hill is because of that mg. If we didn't have that mg in the x direction making it go down this hill, this sled would just be sitting. It just would be not even moving at all. And so we've got that frictional force, and so we see that's what we're looking for, so we're going to add our frictional force to both sides. So we get our frictional force equals mg in the x direction. And so mg in the x direction, can we just leave it like that? Do we know that? No, we don't. So we have to put this in terms of mg. And so we see that mg in the x direction is opposite of this angle right here. So mg is opposite of this angle. So we're going to say sine theta is going to equal mgx all over mg. So we multiply mg on both sides, and we end up with mg in the x direction equals mg sine theta. And so you end up with friction equaling mg sine theta. And so now we can plug that in. So we know that our m is 25, and our gravity is 10, and our angle is 15. And so we end up with 250 times sine times 15 is going to equal our frictional force of 64.7 newtons. So the next thing it wants is this coefficient of friction. And that coefficient of the friction is this mu, basically like how rough is the surface. And so we know that friction is equal to mu times normal, so this mu is going to be friction divided by normal. We already found our frictional force up here. It's this mg sine theta. So now we need to find our normal force, which is in the y direction. So let's redraw that free body diagram. So we've got our normal force going up, frictional force going to the left, and our mg kind of going out to the side like that. And so we see that our mg can be split up into our x and a y. This time we're going to be dealing with the mg in the y direction. So you're going to say that the sum of the forces in the y direction we know equals 0 because it's at a constant velocity. And we've got our normal minus our mg in the y. We see that this mg in the y direction right there has a adjacent relationship. So we're going to say cosine theta is equal to this mgy all over mg. We need to multiply mg by both sides. So we end up with this mgy equaling mg cosine theta. Add this to both sides to get n by itself. And so we get n equals mg cosine theta. Now we know our normal force, we know our frictional force, we can plug it in. So mu equals this mg sine theta divided by our mg cosine theta. Cross out your mg, and then sine over cosine end up equaling tangent theta. So you get mu equals tangent of 15, and that is going to be 0.27, and we know that mu doesn't have any units to it. And so the sled reaches the bottom of the slope, continues on a horizontal ground. Assume that the same coefficient of friction. So in terms of velocity and acceleration, describe the motion of the sled as it travels on the horizontal ground. So we are on this slope, and then we get to be on this horizontal ground. So when the sled is right here, we have got this mg in the x direction pushing it down. But when it gets to this bottom right here, we no longer have this mgx. All right, the only force that we have acting on this is the friction going backwards. And we have this motion going forwards. And so we see that now this is no longer going at a constant velocity. This is going to be slowing down because of the unbalanced forces, because we see that now only x direction of just friction, meaning we have a negative acceleration, all right, because it's slowing down. Now, what does this look like on this graph right here? So we see that on the slope we have this constant velocity, and then they tell us to symbolize, so this is when we get off the slope, this is when we're on the ground, and so at this point we slow down until we reach a stop. And so that's what that problem is going to look like.